so we're going to look at diffusion of dimension. So if we say grid graph of, let's say 30/30, the question is how that thing would be progressively eaten.
Why grid graph? Why always grid graph?
Well, I don't think maybe it shouldn't be grid graph, but grid graph, we at least know the dimension. What is your favorite dimension n for given n graph?
I just prefer using actual manifold like things because it's
Well,
like
that's fine. That's
we
fine.
can
Okay,
analyze the limits of those.
fine. Let's do it. The okay, so what are you suggesting? You're suggesting we pick what we want is some high dimensional graph.
Right. So how many dimensions do you want? I mean, our functions can handle arbitrary.
I know that, but what would you like to pick? I mean, are you going to sprinkle into some high dimensional space, or are you going to?
I'm saying just use, well, if it were up to me, I would use a manifold to graph function. Right?
Okay, fine. Let's do, I don't know, 10-dimensional space. I don't know, pick a dimension. I mean, I'm more interested in the exponential dimensional case because I think that's going to be, I think what's going to happen is, well, okay, so let's think about this. So, okay, go ahead. What are you, is there a resource function that does that?
Yeah, flat manifold to graph.
Okay, well, I didn't write it.
If you don't want curvature.
Flat manifold to graph, brilliant. Okay, what does it do now?
So try maybe 10, well, so first argument you want 10 as your dimensions, number of dimensions. Then say maybe 0.1 as your discretization scale. And then do like 100. I don't know how many vertices you want, but let's start with 100. Oh, that's probably, okay. Maybe you want a larger discretization scale. Okay. If the graph is too sparse.
Okay, all right. So now how do I make that into an ordinary graph?
So that you just want the property spatial graph of that.
Okay, all right. So this is what we were doing before, where we're looking at. So if I the dimension estimator on this. So this is a rather small graph with graph diameter, some tiny number.
Right. So if you want to reduce the graph diameter, you can reduce the discretization scale, which will make it.
I want to increase the graph diameter.
Sorry, yeah, if you want to increase the graph diameter, you can reduce the discretization.
Okay. Can I, if I change that to like 300 or something, and reduce this to like 0.2?
Yeah, see what happens. Okay, so that's just going to form a bunch of low. You can say 0.5. I don't know. That's going to be way, way too dense.
Okay. I wonder if it's a phase transition. I mean, it's some kind of percolation type thing. Does it manage to connect everything?
Right.
But I mean, as an intuition builder, what we are imagining is neighboring. Okay, so the basic idea is, dimension diffusion is, fix the number of atoms of space and potential, fix the number of elements, basically, and the number of connections. And then, but we're then rearranging things. I just don't have this intuition, maybe you do, for how, when you randomly jangle these things around. See, look, the reason I was going back to this crazy grid graph, right, is if what I do, so how do I apply, I want to apply some very simple rule here. What's the most minimal rule? Because I think as you make holes in this, I think it's going to end up one-dimensional in the end.
Well, I mean, if its dimension decreases, I mean,
Well, I know, but I'd like to see that happen. I mean, so what would be a move here? What would be a model? You know, how would we apply? So we take this, right, and we say, you know, we just say, you know, let's say rules triple at rule triple at edge list of this. Okay, great. Okay, so now what I want to do is some kind of evolution. And I think you had got a rule. Well, what's an obvious rule to apply here? So we want to take is it obvious what to do here as a rule? Maybe we should apply that rule that you had before. Should we do that?
Okay. I don't completely understand what that's supposed to achieve, but we can try it.
Let's see. That's a different thing. Are you sending me this rule?
Yep. That rule is intended to be. I mean, it was discovered by acting on manifold-like graphs, not on grid graphs.
I understand.
So I don't exactly know what it's going to do here.
Well, that's why we're trying it.
Don't you want list at that edge list?
Yes, I do. States.
Plots list. Or do you just want the states themselves?
No, that's states plots list. Or is that only giving one? Hold on, we want to give 5 steps, and let's say here grid graph 10, 10. Okay. So what fundamentally happens is it falls apart. Some parts of it end up 0-dimensional, basically, and some parts end up 1-dimensional. So this is an example of where, I mean, just to get some intuition here, right? This seems like an example where basically things disconnect. This was very nicely connected, and this rule is causing them to become more and more disconnected. Do you think that's a fair characterization?
Well, yeah, I mean, it becomes disconnected, yeah.
Well, let's try, for example, we have 5, something like this. What is the intuition here? The intuition here is that edges that were here's a way to think about it. You're at a point. The question is, can you get to another point with a GD-SIG? And the answer is, you are randomly perturbing that GD-SIG to prevent you from, the road is randomly getting blown up, would be my claim.
I mean, that's what graph disconnection means.
No, but it doesn't necessarily, I understand that. It doesn't necessarily disconnect the piece, but it means that so the question would be this. Okay, here's a question. Here's a concrete question, right? We've got a dimension estimator, it's applied to a graph, and then given a graph, randomly delete edges. What does this do to the dimension?
Should we try it?
Yeah, that's what I wanted to, yeah. Yeah, given a graph. Okay, so we want a nice high dimensional graph like your creature here. And then
yeah, maybe try again. Maybe let's try and tune the discretization cutoff so we get something.
I think that wants to go up to like 2 or something.
No. That
the other way.
It's that's going to be way too dense. 1 was already too dense. So if we do like 0.6, I mean, if we just play around with it, eventually we'll find something.
Okay, so I claim there's some percolation threshold here, which by the way is already telling us something, because that's telling us we're going from essentially 0-dimensional stuff to, yeah, I mean, so, okay, so the question would be, is there a percolation-like phenomenon, e.g. a dimension phase transition?
Mm-hmm.
Wouldn't that be bizarre if there was a dimension phase transition in the early universe?
Well, I mean, that's what my paper was suggesting as a minimal model.
Explain.
Well, one way you can, I mean, I was only doing this for mathematical, for reasons of simplifying the mathematical analysis. But if you want to think about decaying dimension in the early universe, kind of the simplest way you can do it is by having a phase transition point where you go from effectively infinite dimensions to effectively finite dimensions. And I was analyzing what's the causal structure of such a universe.
Right. Okay. Well, so here let's look. So we hit a percolation threshold of some kind by 0.75. Okay. So if I were to look here at, I mean, just at that graph there. Okay, this graph here, the 0.75. So if I say vertex count and edge count. Actually, there's a nice, what is the right way to do this? Given that you have those two things, isn't there a nice operator way to apply those to one object? Let's just do it the boring way. There's a nice way to do this with modern functional programming stuff that we have.
It's kind of it's an inverse curry, right? It's currying with functions rather than arguments.
Yes. Which is like through.
Right.
Okay, so this went, I'm a little bit confused. Between 0.7 and 0.75, your system dramatically increased the number of edges.
Right.
Okay. So so you think we should go from here and randomly delete edges?
Right. I mean, well, I'm only suggesting that we want something with a reasonable graph diameter so that the dimension estimator works well.
Good. So let's say first of connected graph components. Not an impressive graph diameter, I would say.
It's better than the other. The other one looked like it was about 2.
Yeah. Okay. All right. Well, so let's take that. And what's the dimension estimator thing for that?
Let's keep it simple. We can do Wolfram Hausdorff dimension.
Okay. I'm just looking at this other code here. So.
So do you want to compute the dimension at a particular vertex or across the whole graph?
Let's put in your across the whole graph stuff. I think we had it from before. Okay. All right. So then, well, I mean, we're going to find the same kind of thing we found before, which was, I mean, by doing this, we had previously had these kinds of behaviors, right? We had this sort of almost linear looking decrease of dimension.
Right.
Okay, but I think there's an analytical way to figure this out, right? So let's just think about what you've got a geodesic ball, and you start, and normally,
But by the way, sorry, just in terms of improving the dimension estimation a bit, after the all, try putting, well, graph diameter 9, maybe put 3 or something.
where for the all dimensions?
No. So just before that, between the all and the all dimensions, just set a maximum, because by default it will use the graph radius as the maximum radius. Try 2. It may just be that this graph is not big enough for. Okay, no, never mind. They're all coming out at about 3.
Well, so I mean, we could certainly do a much bigger. Let's take a look here.
It's dangerous stuff. This thing gets inefficient for large graphs.
What is it doing?
So it's just laying down, points in 10 dimensions and then connecting them if they're closer than a certain cutoff distance with respect to the Euclidean metric in this case.
I think that is nearest neighbor graph. So let's pick some points in 10-dimensional space. So let's say random real.
But it's not nearest neighbor graph.
Why not?
Because it's not connecting to its nearest neighbors.
You're connecting it within radius r, right?
Yeah, so that would be for Euclidean space, which flat manifold graph happens to be. But the general problem involves.
Oh, I know, I realize that, but in this particular case, this thing here might conceivably be considerably faster.
Sure.
So this is saying I want random reals in a certain region, right? So I want to say, I write 50, comma, let's say 5 for 5 dimensions, comma, and then all, comma, 0.05, let's say. Huh. Why am I saying there? Okay, so there's 55 tuples, right? And then I want nearest neighbor graph. All vertices. Okay, well, so let's try 0.2. Oh, I see. This is beginning to wake up. There we go. Okay. So that's given us I don't know how well connected, but that's similar to what you're doing. Is that correct?
I don't exactly know what the coordinatization is here, but yes.
Euclidean space.
In 5 dimensions?
Yeah. Yeah, it's just taking norms, I think. I think it's
no. Of the graph plot. What?
Oh, you mean how is it deciding how the graph plot works? I haven't a clue.
What, like it's clearly doing a graph plot 3D with some coordinates, but I don't know what the.
Oh, the coordinates have nothing to do with anything. The coordinates are just what it picked. I don't know why it picked to do a graph. I mean, I'm sure if I just say graph of that. Huh? I don't know why it's making the thing in 3D. I have no idea why it's making it in 3D. Yeah, it's weird that it's making it in 3D. I can't comment on that. I mean, let's just try something here. Okay, that made it in 2D. So for some reason, it has some heuristic about the uh, number of elements and the names of the vertices and things. Okay. Okay, so let's take a look here. I mean, again, can we just try my little intuition about, okay, we've got a point. It's connected by geodesics to other points. It has to count how many points it can reach. Gradually, there's, it's being bombed. The roads are being bombed in some sense.
I don't know what that means.
It means, okay, sorry. It means we take this and we are randomly deleting edges. Or we could be randomly reattaching the edges to somewhere else. Okay, we're randomly, look, what's happening is
that just means we're applying updates to a graph.
Yeah, that's all I mean. I'm just trying to get some.
We talk about bombing geodesics, right? We just talk about applying rules.
Yes, that's correct. But I'm thinking about the case where the rule simply deletes an edge.
Okay.
Right? And so then my question is, if you simply delete edges, how do you reduce the dimension? Right? If you just uniformly delete edges.
No, I understood, but that was the experiment we were about to try, and then you.
Well, okay, fine. Well, let's try it.
What's your point? I mean, yeah, obviously that will reduce the number of dimensions because the reachability relation is changed.
I agree, but I think we might be able to figure out analytically what it's going to do. That's my point. But let's do the computer experiment first. I'm just concerned that this experiment is going to be hard because of the difficulty of generating large graphs. Okay, so for example,
You're going to test your claim that nearest neighbor graph is faster. I mean, we can.
Yeah, well, here I've got a nice nearest neighbor graph. So let's check. Somewhat bizarrely, this is claimed to be dimension 2. Right? I mean, that's what this would be claiming.
That looks fine. I mean, that looks like dimension 2. But
does it with all of those edges?
You've selected a huge graph radius, a huge discretization cutoff.
Okay, let's go down to 0.2 or something. Okay, that's nice. That's looking very nice. Okay, let's go 300 steps. Okay, great. Okay, I see. The norm depends on the dimension here. That cutoff should be 1 over, right? So the distance between, on average, since these are 0, 1, these are in the range 0, 1, right? That means the maximum norm is square root of 2. So I claim what we really want is something like, let's say 0.5 over square root of 2. Oh gosh. Let's say 0.2 over square root of 2. Okay, fine. So now I'm going to claim, okay, so I claim that's a nice two-dimensional graph. So, and we should be able to get our estimator to say, and
that's more efficient.
Say again?
This doesn't, I mean, try it on 2000 in 10 dimensions like you were doing with mine.
You are being competitive with these poor things. Okay, right, 10 dimensions.
No, 10 dimensions, not 10.
Yeah,
right. I'm just genuinely curious.
Yeah, right. Okay, so we got to get the same cutoffs. What would be the cutoff?
Well, you were trying, what were you trying it with above? You were trying it with sort of 0.75, I think.
Yeah. Okay, let's not live that dangerously first. That was nice and fast, at least.
I
All
mean,
right, let's try.
if there's the reason I'm asking is if there's something nearest neighborhood graph is doing internally,
I think it's fairly fast.
then I can presumably exploit that in the
I
WF.
think so. That's why I'm suggesting it. Right. And I think if this doesn't do it, I think that some of the new spatial statistics things do. And actually, I'm going to point out to them, they probably want to refer back to. Okay, so here, all right, so we've got this graph and it's pretty big. So this graph, let's do our dimension estimator. So let's call this G10. Okay, so now your dimension estimator, does that work on a graph? Yes, it does. Does it?
Yep.
Where was that dimension estimator? There we go. So you recommend that goes off to, well, let's find out the graph diameter of this thing. Oh, piffle, puffle. Okay, so let's say first of connected graph components. Five. It's not very large. Did we have a larger one before? Did we have larger numbers of? Okay, G10 here. Does this use parallelism?
No.
Okay, so we thought this was going to be 10 dimensional, but it's actually 5.5 dimensional according to this. But let's go only out to range 3. Oh, that's weird.
Not really. It uses
Why?
the graph radius, which is ceiling of 5/2, which is 3.
Oh,
That's
well,
that's the default max radius.
okay, fine. Okay.
Bear in mind, you're also, because you're choosing to compute the dimension across all vertices, you're also getting all of the boundary effects, which will.
I understand. Is there any way to get the graph? Is there a graph center? Yes, there is. Okay. So can I feed those directly into this all?
Yeah. So instead of all, just put in a vertex, and then instead of all dimensions, just say dimension. And you can get rid of the vertex method option.
Okay, so I can say first of graph center, for example.
Yeah.
Can I give all the graph centers, or I just do first of graph center?
No, you can't.
Okay.
It's even worse.
Very modest. Okay, so let's just map it over all the elements of that, just so I understand what it's doing.
It's even lower dimensional.
Yeah, but it's curious. It's about 5. I mean, I'm kind of wondering whether if I were to put,
You could try ramping up the 3 to 4 or something. See what happens.
I thought you told me that it was. Oh, I see. It's the default. Is that okay?
Okay, it gets worse if you go to larger radii.
I think it's got, it's sort of falling apart, would be my impression. Yeah, it's bigger there. And I mean, if you look at the coordination number at 1, okay. Okay, so fundamentally, this thing is, it's spraying out quite quickly at the beginning, and then it's kind of running out of steam, and its tentacles are rather sparse.
Right. Well, you should be able to see that. You can call highlighted graph as a property.
In which property of what?
In Wolfram Hausdorff dimension.
Isn't that going to be absolutely scarily large? Well,
Why? I mean, it's no more expensive than rendering the graph normally. Well, slightly more expensive,
but the rendering the graph normally, it's a giant graph. It's got
oh
87.
yeah, oh no, fair enough. Yeah,
I mean, right around that graph center, all we're going to see is the neighborhood graph, right? I mean, basically what we want is the neighborhood graph of G10 around the graph center to step 1. And these are just going to look like, what the heck are these looking like? Oh my gosh, what is it doing?
yeah. I mean, maybe you want to reduce the. I really think you should take down the 0.75.
Yeah, okay. Let's go down to 0.2, for example. What? I'm telling you, this is some kind of crazy percolation threshold. Oh, rah, rah.
There we go.
I guess. I mean,
That looks more promising.
well, okay. So
Just check its graph radius. Oh, okay. Go straight to dimension.
So actually what I want to do is that whole. It's taking its time. Why is it taking so long?
Well, it's probably having to go to a larger graph radius.
Yeah. It should be using parallelism, I think. Wow. Well, let's see whether. Is that right? I just want, that goes root distance 1. No, that's one vertex. Then I want to say all comma 1, right?
Right.
Let's go distance 1. Okay. All comma 2. I'm just concerned that these things are not. I mean, maybe we're just trying to go too high with 10 dimensions. Maybe we should go to a much more modest dimension. But I mean, I'm just trying to think analytically. If you have this high dimensional graph, and you're simply asking, okay, so normally in that ball, you have r to the d plus 1 edges, right? And just a minute. You know, I think I'm concluding that academics on average do no work. Just somehow, like there's bibliography, right? Everybody was saying, oh yeah, we'll help you with this bibliography. And then when they actually realized that it's like thousands of papers and things, and they're just like, well, you know, we did a search in math reviews and here's what we got. And I said, yeah, well, that's the beginning of it, but that's only the beginning. Then you have to do the actual work. Oh, well, okay, no matter. Um, um, okay, let's see. So again, could we just try to go through this logic? You got this ball and it has r to the d plus 1 edges in it. You start randomly deleting edges. On average, what happens? So as you linearly delete edges, I may be being very stupid about this, but as you linearly delete edges, your likelihood of getting to a particular place, let's see, the number of ways you can get to a given place, there's got to be a way to do this. There's got to be a way to figure this out.
As you keep saying, and as I keep saying, I just don't see how you can possibly make that claim independent of vertex connectivity. The whole thing depends on the structure of the graph.
Oh, I'm sure it does. I'm just saying that there may be some.
So how can you possibly make any general statement about it?
Okay, let me think about this for a second. Well, I'm imagining that some kind of diffusion process. I'm imagining that the way you get from one node to another obviously in detail it depends on the structure of the graph, okay? But I'm sort of just hoping that there's a way to get, well, I don't know. I mean, look, I'm hoping for some universality result, basically, analogous to A, the central limit theorem, B, critical phenomena, et cetera, et cetera, et cetera. That's what I'm hoping for. Now, maybe it isn't a real thing, okay? But okay, let's see if we can do the experiment. Okay, so far we have not succeeded in generating a convincing high dimensional graph. So what can we do better for that? Maybe we should not aim as high. Let's aim for like 4 dimensions. Is that reasonable? But by the way, I just want to check something here. Just a simple check. If we put in a grid graph here, my favorite, your non-favorite grid graph, and we perhaps do the centers thing.
I don't have anything against grid graphs. It's just that,
Actually, let's put in a torus graph. I think it's better, right? Because it doesn't have boundary, at least. And here I just want to do that. 1.5. Why is that as low as 1.5? Do you understand that? I don't understand. I mean, I know that there's a bunch of degeneracies in these graphs, right? How do we get a, we can get the mesh graph, right, of a volume. Now let's just see what happens if we just go 10, 10, 10 here. Is it even going to be higher, or is it just going to be something comparable to what we got before? Do you understand that?
I don't really understand what it is you're trying to compute. I mean,
I'm trying to get back the dimension of this graph.
yeah, averaged out across all vertices applied to a graph that is non-geometrical.
I know. Okay, so to try and make something more geometrical, why don't we try, how do you make a mesh graph? Do you know what I'm talking about? Mesh connectivity graph. Does this make any sense? So what I was thinking about doing here is just taking a region and finding its somewhat random mesh connectivity graph.
Right. Just like intrinsic and extrinsic curved manifold to graph.
Okay. Well, we can use those too. Tell me what to do. So, I mean, again, I think this flat manifold to graph thing isn't looking super promising here because we don't seem to be able to generate big enough graphs.
No, you can. I mean, I've done it. It's in the documentation, but it's just you have to use large numbers of vertices and you have to tune the thing so that the graph radius is significant enough.
All right, so let's just look at the documentation then to find that. If you've got this in the documentation, then let's just go there.
Well, there are examples that are produced by these manifold functions in the documentation where you get the right limiting dimension.
Okay. 2 discreteness. Okay, 2. All right, so now this is 3. Okay, but are you saying that this thing here will be dimension 3?
So like I'm doing this experiment now, and I've managed to get on flat manifold to graph. I can get dimensions of about 8 for a 10-dimensional thing with 800 vertices, and presumably if I go higher.
What are the parameters?
Well, if you do say 800 to 1,000 vertices with cutoff of about 0.75, and then you pick. I mean, just
in 8 dimensions.
Sorry.
In 8 dimensions.
In 10 dimensions. The case we were dealing with, 10 dimensions.
Okay. Yep. And then what? Then I pick the largest component.
Yeah, and then pick a vertex. Don't use the graph center because that seems to go badly.
Oh, I need to say spatial graph, yeah. Well, so maybe there's something. Why would there be something special about the graph center?
Oh, hang on, let me see if I can understand this. Oh no, maybe it's not so bad.
Why is it taking so long? Oh, there we go. Okay, fine. So now you suggest that I take this graph.
Right. And then, don't use dimension method mean, which you were using before, but use dimension method identity. And then you can see intermediate values of the dimension.
Vertex method identity or dimension method?
Dimension method identity.
So vertex method mean, dimension method identity.
Well, in my view, you shouldn't be averaging it out across all vertices anyway. You should specify a vertex. Well, first of all, that should be dimension, and also 1 is presumably not a valid vertex unless you call the index graph on it.
Oh, that's because it's 262. That would not help.
Okay, so 6, 5, yeah, okay.
Not a totally convincing display of 10 dimensionality.
it's better than before. I mean, obviously the small radii and the small radii are dominated by discretization effects. The large radii are dominated by boundary effects.
Exactly.
So the intermediate ones are the ones we care about. So we get, about 6 dimensions there.
Yeah.
With higher numbers of, with larger graph radius and so on, you could go higher than that.
Okay, but at these small radii, what we fundamentally got is some kind of wheel graph where there's a center and there are a bunch of spokes, right? And so our first approximation to the dimension is how many spokes do we have?
Mm-hmm.
And, we delete spokes, we'll decrease the dimension. Now, if we go second level out, right? So, I mean, if we say, I don't know, table, 0 goes to I goes to 20 or something, and graph of that. Oh, for goodness sake. Okay, so that's our first approximation. And our second approximation, the most trivial approximation, the dimension is just going to be reduced by whatever the fraction of those that get zapped is. The question is, at level 2, what happens? So at level 2, see, I mean, well, it just seems rather straightforward at level 2. I mean, it's basically what we're saying is, given our favorite, well, let's say torus graph, okay, I think this is a way to think about it. Yeah, look, I mean, this is a way to think about it, I think.
What?
Well, we look at these graph neighborhoods, okay?
Yeah.
And what's happening?
That's how we compute dimension.
Indeed. But what I'm claiming is happening. What's that?
What's the idea?
Okay, the idea is this. At every layer, at every shell here, you're asking what happens if you randomly zap edges.
No, I understand that. What's the idea?
The idea is I think we can compute what the effective dimension is as we, so here, right, in this graph, if we say, up to 4 steps or something, right? So now here, the question is from element 1, we would ask the question, let's see, we just want to know how big, how do we compute the shell? We have to do a graph complement or just a complement of the things that are a certain distance away.
Just do a graph distance of neighborhood graph hash -1.
Fine. What graph distance? But why is that?
Graph difference.
Oh, I see. Okay, so this will be the shell.
Yep.
Okay, dandy. Okay, that's our shell. So my point is, okay, so here's my claim. Let's see if we can just compute this properly.
You know,
Okay.
I understand. Trust me, I understand the setup. You're now going to
I know.
That's what happens to the dimension, and my claim remains the same. That in the, you know, even in the simplest case, you can see that this doesn't work, because if you start from the spoked graph, and you just randomly delete edges, there can be arbitrary degree of redundancy, because I can then connect up the spokes by an arbitrary number of edges. It can either be a pure spoked graph, or it can be a kind of complete spoked graph where every pair of spokes is connected, or anywhere in between. And in the complete case, each random edge you delete is going to have minimal effect on the dimension, whereas in the pure spoked case, it's going to have maximal effect on the dimension. And without knowing the graph connectivity, there's no way to know where in that continuum you lie. So I just don't.
I get it. Yeah, I get the claim. I get that claim. I understood that claim as well.
Yeah. So how can there possibly? So I asked the question again: how can there possibly be any general theory for the dynamics of dimension change in the absence of knowledge about the graph connectivity?
I don't know yet.
Okay.
I just don't think it's as hopeless as you think it is, because I think there's enough. Okay. Okay. The other point is, if we are edge preserving, the edges have to go somewhere.
Sure.
But they're going somewhere local, and that's an additional constraint.
Right. But why couldn't edges why couldn't they orbit? If you see what I mean, like why couldn't you end up with an oscillating dimension?
Perhaps you could. Why am I saying you couldn't?
Because you're saying your claim was that we could define it. The whole context for this conversation was your claim that we could derive an effective theory for dimension change, an equation for dimension change.
Yes.
So if it's sometimes oscillatory and sometimes not oscillatory, then
look. The question is this: okay, is there an equilibrium? Is there a thermodynamic kind of limit for this or not?
Yeah.
Right. If you're saying, look, the structure of the graph affects the outcome, great. I agree. You could say the same thing for, the precession of gas molecules affects the outcome. But because we know typically that we have lots of randomness in the configuration of gas molecules, that doesn't matter much. Mm-hmm. And that's all I'm claiming here, is that if we're in a situation where the configuration of the graph is kind of random, maybe it doesn't matter much. And you're saying there are particular cases that you can imagine where it matters a lot, and I agree with you.
Right. No. Sure. So I could perfectly well imagine that in these, for something like the flat manifold graph stuff, where you have an actual statistical distribution underlying it, there may be. I mean, obviously, it would remain to be shown. I'm still unconvinced, but it's at least plausible that there's some general continuum theory of dimension in those systems. But if you then start applying it to grid graphs and torus graphs and things, I don't understand how that can possibly work.
Okay, maybe it can't, but I think it's worth trying an experiment, because I think that by the time we're zapping edges at random, we will be getting sort of a quotes somewhat random graph. That's my hypothesis. I mean, okay, so here's a question. What happens if you look at the dimension of random graphs? I don't know what let's see. Metric dimension for random graphs, is that relevant? Let's see. Is this relevant or not? Can't tell what this is really about. What is the metric dimension? What does that mean?
Defined in the first sentence of the abstract.
Minimum number of vertices in a subset of the vertex such that all other vertices are uniquely determined by the distances of the vertices. Is that anything related to our definitions of dimension?
Well, yeah. I mean, it's related to our definition of topological dimension. Yeah.
Which is not any of the dimensions that we're using as we take limits.
Well, it is the dimension we're using in the specification of tensor indices.
Okay, is this a relevant paper
For what?
for this question that we're trying to ask?
I don't understand the question we're trying to ask.
Okay, the question we're trying to ask is, given a random graph, we don't understand what a random graph is because it's not obvious how you construct a quotes random graph. For us, operationally, a random graph is a graph that comes out from having a bunch of updates applied.
Right. I mean, yeah, there is a formal definition of random graph in combinatorics, but I strongly suspect that's not what you're talking about here.
That's not what I'm talking about because there isn't. I mean, because it depends on the distribution, right? There are many different graph distributions.
Sure.
Right. And so what I'm saying is, I don't know which graph distribution corresponds to, it's like saying, with gas molecules, eventually you get the Maxwell-Boltzmann distribution, but it's not obvious. And you could just say gas molecules are random, but then well, actually they're random according to the Maxwell-Boltzmann distribution. So, I mean, this probably is stupid, but let's just, we can easily do the computation, right? So we've got this index graph of the, so let's see, what we're doing is this thing here, and we're randomly deleting edges from this, I think. And we're asking how big is the shell? Well, I can do this, but I mean, you're convinced that it's totally pointless. It may be pointless.
I'm not convinced that it's the other way around. Nothing you have said so far convinces me that this is going to work, but you seem very certain that it will, and I'm wondering why.
Oh, I'm not certain it will work. I just think it's worth trying. So let's try it. I mean, so let's see. So what we want is we have a graph with a certain dimension, like let's say 3, and this is absolute nonsense here. This is G and G. Okay. So this is shell size Okay, so vertex count of this. Okay. So what I'm claiming is that if I take the original graph, okay, so here's what I'm claiming. I say edge delete. What arguments does edge delete take? Okay, I don't know how many edges we want to delete. Let's say a fraction f of the edges. Okay, so now we want to say random choice. I forget the arguments for random choice. Oh, actually, I just need to say that. Yeah, and random choice of vertex list of G, comma f times vertex count of G. All right, so it's edge del. Oops. Oh. What? It said a list of edges that I could do. Oh, it's because I'm doing edge delete. Deletes a collection of edges. Oh, maybe this has to say random sample. There we go. Okay, so this is deleting certain fraction of the edges, right? So let's see. The claim would be, okay. So these are what I get from, so I get some version with edge deletion 0. Oh, why is this taking so damn long? It's probably a very inefficient way to do it. Okay, so that's with edge deletion 0. Edge deletion 0.2, I claim these numbers, okay, they're almost exactly the same. Well, not quite the same, but they're very close. Edge deletion 0.4. Okay, so this is my claim, right? That these numbers are that the effective dimension, which is, so assuming these rise logarithmically, so this is ratios that we want. Oh, no, I don't want that. This is the claim. This is going up like r squared. I'm losing my mind here. I want to just take the logarithm of these things and see if it's linear, right?
Interesting. It looks really stable.
What looks really stable?
The dimension.
And of what? So did you just compute something?
Yeah. I ran the. I was bored, so I ran the experiment you were suggesting.
But this experiment, the same experiment. Or
I know I was running it on an actual geometrical thing.
By zapping edges. You're zapping edges.
Right. And
okay.
It looks very robust. Which is...
Okay, I predict it's going to fall off a percolation cliff.
Okay.
Try increasing the number of things you zapped.
Let's keep going.
You want to send me the code so I can run it as well?
Well, sure. I mean, but it's just, it's the obvious thing. I started with a 5-dimensional graph. And then I'm just doing this.
It's your famous word obvious again.
Yeah, I need to retire that. The code is awful, but do not judge me.
Yeah, that's all right. Okay. All right. So this is, what the heck is this doing? Right.
U1 has to be a graph.
G1. No, wait. G has to be a graph.
Oh, hang on. Sorry. No, I sent you the wrong thing. Hold up. Yeah. You want that.
So wait a minute. G1 is a graph here.
Yep.
I can't say that. I have to say module. G1 equals. Well, you're deleting only 10 edges. So I was deleting
This is really interesting.
yeah, what did it do?
I found one that increases when you delete edges. At least for a while.
But these are random graphs gotten from your sprinklery.
Yeah.
You want to share your screen?
Oh gosh, I just screwed something up. Why does it fail if I delete too many? If I do,
Because the graph, your dimension estimator goes totally bonkers.
no, this is an error with edge delete. If
Well,
I
how
do,
did you do it iteratively? Because maybe you've already deleted that edge.
well, no, I'm just feeding it a random choice of 100 edges. But 100 seems to be too much. It works fine if I feed it 10.
Right.
Hold on, come on. Let me recover my kernel. Maybe it'll work. Yeah, okay. Let's run this 50. Ooh, there's a weird discontinuity thing appearing.
Yeah. I'm telling you, there's a percolation cliff.
But the fact that this is so wild makes me more convinced of my earlier skepticism, if that makes sense.
I think it's wild for the same reason. I mean, I think these things are still very small.
Yeah, no, I mean, you're right. We're operating close to discretization scale. That's certainly true.
Look, the question, okay, let's say you're right. Okay. The question is it an infinite parameter space? In other words, there is some continuum description of dimension change.
Right.
Okay. So now we've got graphs, and they've got, you say the graph, this kind of graph has this description. My claim would be that there are a limited number of parameters of those graphs that will determine that continuum limit.
No, I absolutely agree. I mean, so here's my intuition, at least, which obviously could well be wrong. So we know that there are fairly weak conditions that one, GR in our models is a constraint on parameter space. But we know that, if the requisite three axioms are satisfied, then we get an effective continuum theory.
Yes.
The thing that I'm just not buying right now is that the continuum, and as you correctly say, GR is a continuum theory of curvature. In effect, as I understand your claim, it is that the same constraints that give you a continuum theory of curvature will also give you a continuum theory of dimension. And I just don't completely see why that has to be the case.
I don't know why it has to be the case, but the point that I'm making is, if it is going to be a continuum limit at all, so it is conceivable there wouldn't be a continuum limit of dimension change. That seems surprising if true.
No, I agree that there's bound to be a continuum theory. My suspicion would be that the axioms one needs, the analog of the finite dimension requirement and so on, would be different for the axioms one would need to derive the continuum theory of dimension would be subtly different from the axioms required to derive.
I don't disagree. I suspect that there'll be some, the computational boundedness requirement will be strangely different in some way. Mm-hmm. And it could very well be the case that in this sort of, look, the point about mean field theories is they're usually derived by looking at, what would otherwise be dynamics is just random.
Right.
But that's the typical way of deriving a mean field theory. So, statistical. So the question is what, and this is where we run into trouble again with the statistics of, the space of graphs. Because you don't really understand that. And
yeah, sorry, if you don't mind, I mean, I've only been able to compute it a few.
Go ahead, let me go share.
But
please, go ahead.
I'm amused. Because this is not what I was expecting to see. The dimension is going up slightly, but it's still hovering around 4, which is what it started at. It started out at 4.02.
You're deleting edges.
Yeah, I mean, you can see exactly what I'm doing. Like, I'm just each time edge delete G1 random choice edge list.
And you're starting from all possible points.
In computing the dimension, yeah. So
I think for a second. This says from a given point. This is really weird, right? Because you'd usually expect you delete edges. There are fewer points you can get to.
Right. But what matters is not what matters is not the absolute number of points. What matters is the growth rate. So in some way, if you reduce the number of edges in the inner shell, you actually increase the dimension, right?
Yes.
So I
popping out.
Yeah.
Okay, go ahead.
I'm guessing that's what's happening here. It's this edge deletion for some reason. Well, I guess ultimately probably because of boundary effects, is preferentially deleting edges from the inner shells and not from the outer shells.
Yeah, so that's what's happening. It's boundary effect. Right.
Yeah, this is interesting. There's clearly a rich science of dimension change.
Yeah, but we don't have even a single example of how this works. I mean, so let's see. Well, come on. How can we think about this? How can we think about this? You're making random changes to a graph. What is it on average going to do to the dimension?
Right.
And what we just realized is it doesn't go monotonically down.
Right. I mean, it could. But
I know. Might not go down if you are effectively, preferentially deleting from close to the point you're starting from.
right.
Okay.
Oh, this is interesting.
For a second here. Let's see. Here's what I think. I think this is going to be actually more robust. I mean, look, general relativity has basically one parameter, namely the cosmological constant.
Mm-hmm.
How many parameters is this going to have? I feel like there's some way to think about these randomly perturbing a graph and how it changes the dimension, and I'm just not seeing it yet. You know, I should be modern. I've got, now that I've got this electronic thing that I can draw on, that I can make sketches on, rather than just stupid pieces of paper.
This is interesting. So if we only delete one edge at a time, so it turns out by deleting multiple edges at a time, you mask certain effects.
Mm-hmm.
So in particular, there are these interesting discontinuities that appear. So, you know, the thing.
I saw you. Do you want to share your screen? Yeah, go ahead.
Yeah, sure. Well, you can. So these are my intermediate thingamies. So you can see it. There's a sort of monotonic increase, and then a discontinuity, and then a monotonic increase, then discontinuity, and then sometimes there's a discontinuity with an increase. So I assume what's happening here is these are these small monotonic, you know, these kind of continuous monotonic increases are presumably edge deletions that are kind of close to the, you know, close to the point you're sampling from. And then these large jumps occur when you, you know, when you sever one of the spokes, and then whether that spoke occurs close to or far away from the vertex you're sampling from determines whether or not you are, whether you know, whether there's an increase or a decrease would be my suspicion.
Yep. That's what I would assume.
This is really weird, but these look kind of like random walks so far. I mean, if you just follow the, you know, the discontinuities. If I do, like, is there an obvious trend there?
Well, that's interesting because let's just think about this. you know, I don't think it's going to. Yes, I think there is an obvious trend there, which is up, bizarrely enough.
Right. But it can't go up forever. There must come some.
Keep running it. Keep running it. See what it does.
I will.
Start it from the beginning and run it. Right. Just run it. Just run long run.
Yeah. Okay. Fair enough. Let's do that. Let's do this. Let's go 500 or something. This will take a while. I'm not running on particularly sophisticated hardware.
Are you still running on some MacBook Air?
I am. I'm afraid it's my current work laptop.
Oh, for goodness sake! Why don't we just send you a better computer? I mean, these look honestly, these other computers aren't that much faster, but it's a factor of 2 at least.
Yeah. Well, I mean, I do in principle have access to a supercomputer I can send things to, but often it's more trouble than it's worth. If it's particularly for smallish jobs. I don't know. Maybe we should switch back to your screen, and I can.
Well, no, just send me the code, and I'll run it on because I can run it on my big.
Okay, yeah, that's fair. So I mean, all I'm doing is, well, you can take this.
Okay, if you unshare your screen, then I can. Oh, you've got another weird thingy here, pure spatial graph. I didn't imagine what that is. Okay.
Oh no, so that's spatial graph in lower dimensions will attempt to coordinatize. Pure spatial graph just returns the combinatorial structure.
Okay. All right. Okay. So this is GI5. Let's call it as the initial graph.
Okay. Yeah. So then, wait. Let me modify this then. So GI5. All right. Well, in that case, you should just be able to run that. Why are those quotation marks not working?
Who knows? But here, let's just write this a little bit better. So, I mean, let's just take you're doing sequential edge deletion against this random choice, right?
Right. Undoubtedly, there's a way of nesting that.
Right. But what I would do, why don't we just do this? Why don't we just say edge delete fold list edge delete hash comma hash 2, which isn't worth saying, but GI5, and then say random sample of edge list GI5. Right, so that's going to give us all the way down to nothing. You can just take, well, actually, we just say random sample. But that's going to go all the way. Let's say take up to 100. Okay, so that's, so for each of these, we're going to apply this thing, aren't we? Are we?
Right.
What's that range of 100 doing? That's just, oh, that's just you computing.
Yeah.
Okay, so this is, so what we're doing here, this is the fold list, which is taking destroy graph. Okay, and this will be destroy graph okay, so now we say destroy graph GI5, comma, let's say 20. And then just to check that it's actually working, let's say vertex count of those. Well, that's not a good sign. Am I doing something stupid here?
No, that's what you'd expect, right? You only lose vertices very occasionally.
Oh, right. So if we say edge count,
That looks pretty monotonic to me.
yep, okay. Okay, differences of that. Great. Okay. All right. So that's the edge. Okay, so that's what's going on there. Okay, so now we want to apply this thing, right, to each of those. Correct?
Yep.
So these.
Yeah, something's got screwed up with the quotation marks there.
Okay, so this. Okay, so that's the thing. Yep. So let's say parallel map of that against destroy graph GI5, comma 100. Splafferoo. Something went wrong. It's rather weird, actually. I mean, there's something, it crashed one of the kernels. What are those doing? Okay, but this is basically not changing the dimension.
Right. You've only done it for 100 edges, though.
Right. Well, how many do you think I should do it for?
Well, I mean, the graph has like nearly 9,000, right? So,
all right. Well, let's try it again with let's say, let's do this. Let's say destroy graph.
but yeah, actually, now that I'm thinking about it, this does seem to make sense, right? That most of the time you are not, you're going to be selecting edges from closer towards the center of the ball than closer towards the extreme of the ball.
Why? It makes more of a difference if you sample them at the center. That has a kind of more leverage.
Yeah.
So when you delete them at the center, you are leaving, the periphery is more likely to be left intact, right? When you delete edges in a ball, the fraction of the periphery.
Right. There's just more center than not center. And the point is, if you do delete from the center, the dimension will go up.
I was thinking it the other way. I mean, there's the fraction of the periphery that is removed is much less than the fraction of the center that's removed.
Yeah, exactly.
i.e.,
more of the center gets removed. If you flip that.
Oh, I see what you're saying.
Equality the other way around, which means that the dimension will go up. So what I would therefore expect to see is a fairly robust thing, is that the dimension will go up and then you'll hit the percolation threshold and it will crash.
There you go. Well, that's going up to 100. So let's look at it for a bit longer. Okay. So let's go up to, so what we'll see here is up to, I don't know how many edges we had Here, let me just go. i.e., there will be a higher dimension, not lower. Well, so much for our intuition there. We got that wrong initially.
Right.
That's all right.
Well, that's an interesting sort of.
Yeah, it's interesting in its own right.
That's an interesting cosmological scenario, right? Is that
you randomly delete edges.
That effectively dimension increases rapidly, and then you hit a percolation threshold, and it decays.
Yes. Although I think that this random edge deletion is not the best model for what's happening.
No, sure. Actually, random.
You're thinking of random vertex deletion. I don't know whether that's right.
No, I was actually thinking of what's going to happen with random edge addition.
The reverse of this, methinks.
Yeah, it seems plausible.
I should be running this in the newer version because I think I can do. Okay, this is going to generate a picture. Okay, what are we predicting is going to happen? Eventually, this is going to crash, right?
I think it has to, yeah.
I don't know why it's taking it so down.
How could it not? Okay, what could happen that would make it not crash?
But it'll get very fluctuating, for sure, towards the end. Oh, for goodness sake.
Frankie.
Okay.
Oh, I'm seeing threes.
Yeah, but look at this. What the heck's going on there? Why did it?
Oh, graph radius infinity.
Oh, that's what went wrong. That's what went wrong. We have to keep connected components.
Yeah.
Right. Okay. So let's go. Let's hack this out.
But that's already
boom.
Oh my gosh. Look at that.
Poor universe.
That's great.
Yeah, it's really amusing.
That looks like a phase transition to me.
Yes, it's a percolation transition, I think. And I bet what's going to happen is there are going to be multiple ones of these. It's going to step down.
Yeah, exactly.
It's going to keep stepping down. It's going to keep going. It's bubble up and then it steps down.
Yeah. Which I mean, actually, that's already kind of interesting because that's you see that at a micro scale anyway, right? Because you saw that with there were mini steps.
Yes, right.
Already. So there's some kind of self-similar, like discrete self-similarity.
I think so. So hold on. Let's think about this for a second. So then, let's deal with this idiocy here. Okay, so let's rewrite this for a second. Okay, so destroy graph basically has to say each time. Let's do this again. Destroy graph X. X hates it when I do that, but anyway, is edge delete is first of graph connected components. What did I do wrong here? What am I doing wrong here? Oh, first, I forgot.
Yeah, there's a closed bracket.
Okay, let's try this again. Actually, you know what I'm going to do? I'm going to start this in a new kernel. Hold on one second. I'm going to start this in 12.3. Why not test the product at the same time as we're doing everything else? First bug, it loses its oh, come on, you can't be serious. Hold on one second. No. Just a minute, I need to report that. I have to say, so far, my medical report is that I'm having absolutely zero side effects from this. Zero effects. I shouldn't say side effects. I don't even know what effect I'm having, but
You can't feel your immune system getting stronger.
I cannot. And I have a very aggressive immune system, which usually gives me these very high fevers and probably some whole cytokine cascade and who knows what else. And all I see here is that my continuous temperature trace is gradually stepping down, presumably because it's getting later in the evening here. And presumably my, whatever it is, levels are.
I remember you telling me about your legendary sort of 40-degree fevers and things.
Yeah, I don't know. I don't know Celsius, but 104 Fahrenheit.
Oh yeah, I must have done the conversion, but yeah, I remember it being quite high.
Right.
Which presumably is bad news if you were to get COVID.
Indeed. I'm well aware of this point because it's it's like so many things. It has both good and bad features.
Right.
Okay. Let's go here. All right. So now what we were doing here was this was our 5-dimensional creature. And then what we want to do is say parallel map. Wow, why is it taking it so long? Okay.
Yeah, this is really interesting. So presumably we're going to see one of those cliff faces every time there becomes a subgraph that effectively becomes disconnected.
Yes.
Or like, I mean, not actually graph disconnected necessarily, but disconnect. No longer in the shell of some radius from a particular point.
Just a minute. This is not helpful because I don't have all my kernels connected to 12.3. And oh, come on, what is that? Oh, the connected component was missing a particular edge. You see what I'm saying?
Oh yeah, I see what you mean. Yes. Okay. So actually, what you want to do
is reselect the edges.
Yeah. Or I mean, can't you map first of graph connected components over destroy graph X as a post-processing step?
No. Well, I guess I could, but it could waste its time. Yeah, that's fine.
Right.
We'll do
Yeah, I
that.
mean, it would waste time deleting stuff in the non-connected piece, but
Right.
sorry, I was thinking for a moment that there's a curved space-time description of your kernel setup.
Hold on, I want to hear about that, but just a second. Let me just what happened to the status display for parallel map? Okay, so your point is we can just take. Yeah, I guess that's right. I mean, it could, this could be a little bit confusing because it could stop. I think it's better to just do a
Well, no, all you'd have to do is map first of graph connected graph component, sorry, and then do a delete duplicates. That will get rid of the wasted effort.
I know, but the alternative, which seems perfectly reasonable as well, is to do a random choice. Look, I think this is a better way to do it. I just say nest list of this thing here, where that is random choice of edge list of hash. See what I'm saying?
Right.
And that's just T. And let's just do it for 100 just to check that it's working. Okay. All right. I wish this thing gave a. Unfortunately, I'm only running on 28 kernels here because of poor technology. Okay, what's the code space interpretation?
Oh no, I was just thinking. So you've got this collection of parallel kernels, but their clocks are not synchronized. So you've got a mixture of kernel-like and time-like separations.
Yes, that is interesting, isn't it? Okay, why is this so damn slow? Okay. Again, I suppose I can go back to you know what? I'm going to go back to the other version. I can't even kill this. Come on, kill it. Okay, let's go back to this version. That. I've now gotten so allergic to parallel map monitor because it really screwed me once. Let's see if I go 50 steps there, then it'll, you know, I don't go 20. Okay. All right, so this is just running. All right, so what we expect to see as a bunch of subgraphs disconnect, the thing will no longer be able to get as big, right? As you go out from a point, there'll be.
Right. But it's not necessarily, like I was saying, it's not necessarily subgraph disconnection. A subgraph might not become disconnected in the graph theoretic sense. It just may no longer be reachable within, a path of n.
Yeah, I understand.
It's kind of local disconnection. I don't know what we call that. Uh-oh.
What the heck is that? What the heck is that? Maybe I need to say edge count -1 or something here.
Yeah, that does seem to be that's a final case problem.
Oh, silly me. Silly me. Think. Because we're doing first of connected components in here, the thing might ploop out. In other words, it only needs to go, it's actually a nest while list, right?
Right. It doesn't go all the way to edge count. It goes.
Right. It needs to go to edge count of hash is greater than, let's say, 1 or something.
Yeah. So the T is now kind of redundant.
Well. All right, let's leave it out by default. Okay. Oh, come on, you silly thing. Okay. Now, do you have an analogy for this? This is like synchronization with light signals.
Right.
I'm telling you, as I think about this economic stuff, I'm, it's gradually improving my intuition about a bunch of these things. I think it's a fascinating, just in terms of a conceptual approach, this business about applying these ideas across all these different fields, I think it's a fascinating way to develop intuition. Kind of unexpected. All right, let's see if this errors out again. Let's see whether this just goes. I think it's going to go blump, 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 and then it's going to go random. It's going to just become very noisy.
Yeah. It'll definitely get less smooth. But yeah, I think we agree that it's going to be it'll be gentle monotonic increases, or more or less monotonic increases, punctuated by cliff faces of sudden decay.
Right. Now, to some extent, the way these dimension estimators are working, they're kind of sampling very broadly here.
Right. Yeah.
And this may be some sign of some, there's sort of schisms in the universe. Oh, look at that lovely thing.
Wow. That is so cool.
It is. It's really interesting.
Oh, look, the climbs get more steep.
Yes, that is interesting. But that's because there are fewer edges there.
Yeah.
So it makes more of a difference.
Wow.
Well, maybe that's the beginning of the universe. Who knows?
Well, hopefully not right at the end there.
Yeah, well, we get pancaked at that point. Okay, so let's just think about this for a second. So what this is saying, if we look at these jumps, the probability of a jump.
Is it just me? Am I inventing things that aren't really there? Do those jumps seem to align quite well with integer values of dimension?
You mean that jumps by an integer?
Yeah, it seems to jump from about 4 to about 3. And then if you look at after two jumps.
I'm unconvinced.
Yeah,
I'm
yeah,
unconvinced.
probably not.
But let's try running. Okay, so this is a case where this case we started off from this GI5 thing, right? So if we do the same thing,
but I'm also really curious. I mean, well, there are a bunch of things. I want to know how robust this is against different. If we just computed the dimension at a particular point rather than averaging.
yes.
But also, I'm wondering if we tried it for other estimators, what's likely to happen.
Well, let's try it just for 1 point. Can we do it for 1 point here?
Yeah, but you'd have to make sure it's a point that always stays inside.
Right. It's going to jump around. The points are going to jump around.
Yeah. But I mean, you could do just at each step, you could just do a random choice on the vertex list.
I know, but that's going to just be noisy. Yeah. I think another thing we should look at here is we don't go out as far. Look, let's not go out.
Alternatively, it's going to return way more data, but you can say vertex method goes to identity, and it will return the dimension at each vertex for each thing.
Right. But let's try just saying, here's one thing I want to check. If we just put a 1 there, right?
Yeah. That's going to be very, very discretization dominated.
I know. But let's just see what that does. And then we'll, because that's going to change the graph, and we'll just do the 2 case if we can.
Well, presumably this is more, the 1 case is much more likely to be just a monotonic downwards thing, right?
I would think so. It'll just be deleting stuff.
One would assume.
Actually, it's not so totally obvious because it could delete its anchor point.
Yeah, but that'll be rare. I reckon this will be a monotonic downwards.
All right, well, we'll see. But let's try to understand. Okay, so my guess would be as we increase the initial dimension, nothing very different will happen here. This will be the same type of behavior.
Right.
But the most interesting thing, as far as I'm concerned, well, first of all, the jumps are interesting. Although the jumps, I mean, up. Well, that was amusing. Okay, I don't quite understand why it has that.
I think that kind of makes sense.
Because it's like a black hole that's about to evaporate. I mean, it's not got as much stuff in it, and so it makes more of a fractional difference.
Right, exactly. Each edge you delete has more effect if.
Right. So, but do we expect that to be an exponential effect?
Well, yeah. I mean, the dimension is an exponential.
No, I understand that, but I mean, do we expect this to take off? That if I look at that curve, is it eventually going to become exponentially fast?
Well, yeah, like I said, the dimension is an exponential quantity. So yes.
I see what you're saying. As opposed to a log. I mean, because this is looking at Oh, that's interesting. So in other words, these estimators for a fixed number of things. Do you understand this?
Well, in order for you to, yeah. So in order for you to get to the point where you get these, increases and then jumps, you need to be going out far enough that these kind of boundary effects become relevant, right?
Yeah. But then isn't this a better representation of what's going to happen in the actual universe locally? I mean, isn't this a better representation of dimension change?
Yeah, probably.
So, okay, so what this is doing is let's just look for 3, for example.
And note also that the estimator is at 5 rather than 4 when you only go out this distance. Again, because you're not dominated by boundary effects.
Yes. So this finally is dimension change.
Well,
This finally is a nice
dimension change too, but this is dimension change without boundary effects.
right. But are you sure this isn't due to like pieces of the universe breaking off and things?
It might be, but it doesn't have to be. Like I say, it doesn't have to be breaking off. It can just be breaking out of the influence. Well, I suppose if it's a global thing, it has to be breaking off. Yeah, yeah, because you're doing vertex method mean. So yeah.
So this is basically okay. So probably the jumps are due to pieces of the universe breaking off, which, by the way, we certainly don't know didn't happen in the very early universe.
Right.
I mean, since we think it might happen for a supercritical Kerr black hole in the current universe, why shouldn't it happen in the early universe?
Yeah. Another thing I'm quite excited to see with these gravitational collapse models is a physical collapse to extremal Kerr.
Sure.
Because then we can actually see.
Oh, what is going on here? Just when we thought we understood what was happening.
No, I mean that makes sense, right? That as the radii get bigger, you're getting closer and closer to the to these kind of stepped solutions because the boundary effects become more and more significant.
I know, but why is it going up? All of these have gone down. Why is this one going up?
The same reason it goes up previously, right? That's.
Yeah, I'm just a little unconvinced that these ones. But basically, what we're seeing is
No, I mean
surprisingly, yeah.
This is why is that? Why is this not obvious? I mean, so for the 2 case, you've got you've got the immediate vertex neighbors, and then you've got the vertex neighbors of those, and there are going to be far more vertex of the second collection of vertex neighbors than the first collection of vertex neighbors, right?
Mm-hmm.
So if you delete an edge at random with overwhelming probability, it's going to be in the outermost shell rather than the innermost shell. The only way you can get an increase in dimension is if the edge you deleted was in the innermost shell. But once you have more, if you have say 3. Now, probably the graph rate.
Yeah, all right, you're right. You're right. There's no inside when you have this fewer edges.
Exactly. Or at least the inside is tiny.
Right. For the above radii, the inside is too small to get zapped. So by the way, talking about time in these pictures, so this is 1 zap per, I mean, our usual notion of our sort of usual foliation story, I guess it doesn't really matter. I guess that we're not reducing the number of degrees of freedom here. So it's not going to affect, it's just going to be a scaling.
Right.
So this is a representation of, okay, so if we were to take, what would happen if we were to take an exponential dimensional initial condition? Can we generate one of those that's reasonable?
I don't know what that means.
Well, I mean something where starting from a given point, the number of nodes in a ball of radius r goes up like 2 to the r or something.
I see. Okay, so it's not exponential dimensional because there.
No, I meant it's
just an exponential volume.
Yes.
Okay.
Such as infinite dimensional in some sense.
Right. Exactly.
The question is, we could generate one of those and see what this does. But you see, look, the thing that I find interesting about this, okay, so this is linear increase here. I wonder if it's going to go on being linear. Should we just try? Let's just try the 4 case here. I think it is going to go on being linear, he says. It's always been linear. Everything we've seen, it's been sort of linear. Well, blah, blah. As the universe gets smaller, which happens when these pieces break off, why is that? But notice the sort of the smoothness of this curve. This has got to be a computable thing, I have to believe.
I'm not sure that I follow that logic. All computable functions are continuous, but not all continuous functions are computable.
Sorry, I got distracted by something. Hold on a second. Oh, look at that. Okay, that's exotic.
Doesn't look linear.
Okay, do you think if I go to 5, it's going to look like, do you think it's going to be the next, like, you think this is quadratic and then cubic? What's that?
We might get 2 steps, if you see what I mean. I mean, you might get another cliff face, possibly.
Maybe. Sorry, but so, I mean, what I was thinking about here was, if we go to like, well, okay, if we can figure out how to do the infinite dimensional case, that would be nice. But if we go to like dimension 8, will these parameters still work, or are those parameters not going to work?
Yeah, I mean, the parameters often have to be tuned to, well, let's see.
I think
Interesting.
Yeah. Well, okay, big picture here. We've got our first kind of vague sort of mean field theory approximation to dimension change. Not probably that good. What do you think the more real version of this is? When if you take an edge and you're essentially taking that edge and you are randomly rotating it around. Go ahead. What were you going to say?
Well, I think what you want is, okay, if we want to approximate the dynamics of an ergodic Wolfram model rule, what we want to do is there's a finite probability of edge deletion. There's of spontaneous edge deletion like this. There's a finite probability of spontaneous edge creation and a finite probability of edge permutation. Or, I mean, like edge endpoint.
Right, but the problem is edge creation is only local.
Yeah.
So we have to be able to do.
Well, edge deletion is only local.
I know, but edge creation is more difficult to implement locally. Because how do you decide which edge to add? Right? Which edge to delete, you just zap a random edge. But an edge to add, it's like you pick 2 nodes and you're, deciding where, which 2 nodes are you going to now connect?
No, I mean, surely it's just you pick a vertex And then, there's a probability of generating a new vertex, or there's a probability of connecting it to a pre-existing vertex.
I know, but which pre-existing vertex? It could be on the other side of the universe for all it knows.
Yeah.
But that's not what normally happens in our models. Because the structure of our models is local, that vertex will typically be connected to a vertex that is not a very big graph distance away.
Yeah, it's graph local, but it's not spatially local. I mean, sure, you would only connect it up to vertices that lay within a graph neighborhood distance of whatever.
Right.
Um,
Right, which is then going to gradually. Okay, so let's think about that for a second. I mean, at that point, you might as well just be running the rules, pretty much.
Sure. Okay, I've. In case there was any doubt, I've just run this for a lower dimensional, for a two-dimensional thing, and we see the same kind of stuff.
How would I? So I want to just say, what would happen if I just ran it on my favorite torus graph? Oh, look at that. There's the torus graph. There's the 2020 torus graph in 2 dimensions. Actually, I don't even need to do this. Oh, actually, no, that was very wrong. Okay, so the same behavior is seen, very close to the same behavior is seen in a pure 2-dimensional torus graph. Modestly supporting my universality claim.
Is this the same behavior?
Well, this is finite distance. This is distance 5.
Yeah.
Looks rather similar to me to that.
But I mean, the torus graph function isn't monotonic, whereas more clearly non-monotonic.
Well, it's got little glitches in it, yes, but it's much smaller graph, I think. Just a minute, I'll be right back. Sorry, hi.
Hi.
By the way, I noticed that these things they're close to dimension 2. Look at that guy at the bottom there. That's the full dimension estimation for the torus graph.
Yeah, which doesn't look that similar.
No, it doesn't. And I mean, towards the end, presumably.
But that may have to do with the
it's boundary.
Yeah, exactly. The property mentioned earlier. There's no boundary. Yeah, I mean that's an important thing to test, right? Is compact versus non-compact manifolds. What happens?
Right.
This is cool.
But there's no boundary, but it has, but it never reaches its full dimension potential, so to speak. Why? I see. There are lots of paths going around the universe. That's what's happening. And the problem is it gets confused, right? Because if we look at, I mean, in your computation here of dimension, you're completely including the paths that go around the universe.
Right.
Whereas here, all right, so if I were to go to, by the way, can we figure out a good, hold on a second here. Can we figure out a good way to get sorry, just a second. A good way to get an exponential, an infinite dimensional thing. I mean, a tree is clearly what's the more homogeneous version of a tree? No. What's the compact manifold version of a tree?
Right. It's. I was trying to work that out. So I mean, it's something like. I mean, basically.
It's like that Sapinski thing.
Yeah. Well, I was trying to work out. What you really want to do is generate hyperspheres of progressively increasing dimension, and then glue them all together, right? With the lowest dimensional one at the center, I think.
Well, it's easy to generate hypercubes, but
well, and hyperspheres.
Think about that for a second. So basically, yeah. You know, it's a pity that in this year there really hasn't been that much progress on these questions about sort of bigger mathematical interpretation of dimension changing stuff. I mean, we've been chugging forward, seeing how to generalize some things, but there isn't a sort of big mathematical theory of varying dimensional stuff that I can see. Or do you think you've spotted that?
I don't know. I still think the general outline I proposed is not. I think it's. I'm not claiming it'll work. I think it's
Which
one
general outline?
The one that I put forward in the first relativity paper, of essentially using sort of universal covering maps as a generalization of coordinate charts and atlases. So and using that to essentially define the dimension analog of of curvature, in the sense that, okay, so you define a connection, some generalized notion of a connection in terms of a universal covering map, and then you can measure the degree to which that connection fails to be exact, and that gives you essentially a way of measuring dimension anomaly, like you would measure curvature.
What is a universal covering map?
So it's a map from a covering space onto the space that you care about.
And what's the covering space for our space?
What's our space? I don't.
Okay, so what do you mean by the covering map? So we've got a hypergraph. What's the covering map for that? And what's the covering space for that?
Well, it depends on the topology of the hypergraph.
But qualitatively, how should I think about a covering space for a hypergraph? Is it some? I don't understand, because I don't understand what covering spaces are. I can't parse that definition.
Okay, so all that's happening. Okay, so you've got some nice, smooth, surjective map from a base space onto your topological space. Sorry, from the covering space onto your topological space.
Okay.
The topological space has the interpretation of a base space, and all you want is for it to be the case that for any point in the base space, which for us would be the hypergraph, there's an open neighborhood, such that the pre-image of that open neighborhood under this covering map is a union of disjoint open sets in the covering space. So for us, that's just it's very much, as I say, it's very much analogous to how we define a connection, which is kind of how this formal analogy arose.
But I still, I mean, roughly, it's something to do with when you do these maps, you're getting some set of clumps. I don't understand. I don't have a good intuition for what this is. But, well, anyway.
Okay, I mean, you know our intuition for the connection.
Remind me about what. So,
well, the connection is just the rule that maps collections of geodesics in a base space. So for us, that's a flat manifold graph of a non-curved space, Euclidean space, onto geodesics in the hypergraph, such that in particular, such that geodesic balls in the base, in the base manifold can be compared to geodesic balls in the manifold in question.
All right. Yep.
That then allows us to compute curvatures.
Yep.
So all that's happening here is the analogous thing, but you're not, rather than mapping geodesics, you're mapping open sets, which for us are the are the balls.
Yes.
And so all you're saying is that the pre-image of any open ball, which I mean, any arbitrary ball in the base space, is given by a disjoint union of open balls in the covering space. So it's just like the definition of a connection, but with some additional kind of multiplicity.
I understand the definition, but what I mean.
And so in the same way as our definition of a connection lets us set up parallel transport and define Riemann tensors and things, we can define all of the analogous quantities for the universal covering map. But that, rather than telling us information about curvature, this gives us information about dimension. And effectively, my sort of conjecture was that there should be a way of essentially developing a theory of differential geometry, or a theory like differential geometry, that operates in this slightly more abstract context.
Using what kind of mathematics?
Well, using this, the kind of usual algebraic topology type methods that people use for analyzing, covering spaces and things.
So why haven't we made more progress on this? I didn't know you'd managed to formulate it that. I mean, I don't completely understand this, but why have we not made more progress in that direction?
I don't know. I mean, I just
because nobody ever reads any of our papers.
I'm not sure if it's just that. I mean, it's just this. Well, I mean, like we've had, that's been on, at least on the winter school list that I put together. That was on, there were a couple of projects related to that just, no one picked up because, right. Well, I think in large part it's because we've been targeting physicists.
I know we need mathematicians.
Where I think we should be targeting mathematicians at least as much.
Yeah.
And actually,
go ahead.
No, I was just going to mention, I at some point I want to discuss this idea in more if I can, because as I say, just right now there's just a slightly more or less an offhand remark made in the relativity paper about how this might work as a speculation. At some point I want to formulate it a bit more precisely and then discuss it with Todd, because I know this is kind of close to his own field of research.
Yeah, he might be a good person to try and figure this out. I mean, right, we also need to figure out what subfields of mathematics are kind of ripe. I mean, there's topos theory and things like that, but I'm just kind of wondering what subfields of mathematics.
I mean, and by the way, that is okay, it's entirely unsurprising that it worked out this way, but that is the one area of mathematics where there are people, I mean, like just today, hang on, wait, I got this email from this guy that Xerxes and I have been in contact with, Carlos Zapata Caratala, who's a sort of category theorist based in the UK, who, is trying to help us work out some of these category theoretic, topos theoretic aspects of the models. So I think the higher higher topos stuff is one of the areas where progress is being made. And it's, again, as I say, it's unsurprising that's happened because we sowed the seeds for that in some sense. So I think, the reason why category theorists are able to kind of get their teeth into it is because we gave them something to get their teeth into, right? With the ZX stuff and with subsequent work. The problem is with these other things, we haven't yet given, I mean, as I say, apart from this rather cryptic remark in one of my papers and some of your suggestions, I don't think there's much for if we brought in a card carrying algebraic topologist or something, there's not a huge amount for them to get their teeth into yet.
Right. I think fair point. A
bit of initial stuff.
All right. You should probably go. I should go. We'll let this run. It'll be in the thing will be, I don't know how long it will take to run.
We should do some more live experiments on this though, because it's.
Yes, we should. All right. Well, maybe we can, let's see, maybe next Tuesday we can book this. If, I don't know what day of the week it is today. Oh, it's Thursday. Yes. Yeah, sure. Let's do it next Tuesday. Let's talk about this. I wonder if we want to bring anybody else in particular in. Maybe Todd. Maybe Todd has things to say about this. I don't know, but look, my basic, yeah,
Am I remembering correctly? I mean, Todd's background is sort of algebraic topology, geometry type stuff, right?
somewhat related to that. I think his thesis was on, yeah, that general kind of thing. And I think it was on some kind of a generalized octonian something or other thing,
Okay.
which is more algebraic than that. But he knows that stuff. But look, I mean, zooming out for a second for the big picture here, I think there's going to be some, somewhat vaguely universal dimension evolution. I mean, there's the analog of Friedman, Robertson, Walker for dimension change, which probably will have some assumptions like FRW has, isotropy and homogeneity and so on.
Right. No. On that, I completely agree. That seems plausible. I'm just, my suspicion would be they'd be slightly different from the assumptions we need for for the GR effective theory.
Oh, I agree. I don't think that yes, I don't think, because I think it's going to transition to being, in the cool down phase, things will be, I mean, what's the analogy? Well, okay, but just talking about it physically for a second. Assume there is some degree of universality in this. Then the next question is, what do the fluctuations look like? In other words, what's the first order perturbation theory of this thing?
Right.
And then, I mean, how on earth does this relate? I mean, I think this rather trivially, I mean, it solves the kind of the problems that inflation was supposed to solve. Do you agree?
Sure.
That's what it looked like back 25 years ago or something. It was because looked at in terms of your back projection of conformal time and so on, it's like everything can see everything.
Right. I mean, yeah, as I went through in the paper, as long if such a phase transition in dimension occurred, then it does solve the horizon and flatness problems.
I know, but you don't need a phase transition. You just need the fact that at the beginning it was sufficiently, it was essentially infinite dimensional, and then everything can see everything.
Right. No, I understand intuitively how it works. Yeah.
Right. But then, although it would be nice to see those sort of conformal, the light cones and so on doing their thing. Because what that means is, what this is meaning, what does it mean? It means if you draw the edges of light cones, that what's happening is, as you go back, well, okay, so this is related to your variable speed of light way of thinking about it.
Right. I do understand the conformal structure.
Well, explain it to me then. I mean, what's it going to look like? There's got to be a diagram. What's that?
The point I was making was that the third feature of, the third undesirable feature of lambda CDM, which is magnetic monopoles, it's less clear how that works. That was the one part of that I neglected in my analysis.
Wait. I didn't even know that lambda CDN had in inflation. What's that?
One of the nice features of inflation is that in principle it smooths out magnetic. It helps explain why there aren't magnetic monopoles. Oh, look.
We finally got an answer. Okay, so let's see. What does this look like? So this is.
Wow, it goes up 1.5 dimensions.
Yeah. But that's to be compared to. Okay, that's to be compared to this. So very nicely, it's close to 3-dimensional here. It goes up. What up? This is freaking weird. And then there's a dimension crisis associated presumably with the size of the universe. I think we need to get more realistic simulations. I mean, this is interesting, and I'm.
Anyway, with regards to the thing I originally emailed you about, my plan was once I'm a little bit further along with this gravitational collapse stuff, and I have some more robust results on the massive collapse, massive scalar field collapse problems. What I want to do is to start off with a graph in high dimensions with an inhomogeneously defined massive scalar field, and then let it do dimension cool down and let the scalar field evolve, and then see what effect that has on, essentially primordial black hole formation, because that's something we can actually compute.
No, it's a good idea. Explain to me the monopole thing again. What is the monopole issue? That I think is after my time.
Oh, so I mean that idea is just, early universe should contain magnetic monopoles.
Genuine magnetic monopoles?
I think so. Again, I don't understand the quantum field theory in any detail.
It's an interesting claim.
Supposedly they're a robust sort of generic topological defect in lambda CDM cosmology, just like cosmic string defects or whatever.
Okay.
So the question is,
magnetic monopoles are in the Higgs field or magnetic monopoles in the electromagnetic field?
I think in the electromagnetic field.
It's much more bizarre. Okay.
Yeah, and then the idea is that one other feature of inflation is that it will smooth those things out. So the magnetic monopoles will be very weak by the time,
Well, there aren't magnetic. I mean, nobody's observed magnetic monopoles.
Well, yes, right, exactly, and this would explain why, right? Because they get diluted to the point where they become unobservable.
Look, the fact is, the standard, in order to get magnetic monopoles, you get those from anomalies.
Yeah.
I don't know. It's actually something I could have worked out back in the day, is the temperature dependence of the anomalies. Didn't think of that. Well. Well, okay. Who knows? Maybe I would have been so excited by that I would have stayed doing particle physics all these years. I was doing this live stream thing a few days ago, and people were asking me about some random result from CERN, and I was remembering it's about some weak decay process, and I was talking about
lepton universality seems to have been violated at LHCb.
Yeah, right. Well, it also seemed like there was strangeness or flavor changing neutral currents, which is another no type thing. Anyway, yeah, I mean, it wasn't a very big effect. I was
I think it's 3 right now.
Yeah, I know, which is nothing.
Yeah.
Nothing.
It's hard to get excited about.
Right. I think it has a high probability of going away. Although it would be exciting if but anyway, just I'm sorry, back to this for a second. I mean, there are all kinds of weird topological defects in, for example, the Higgs field that should develop in the early universe. That part I know.
Right.
And domain walls and cosmic strings and all kinds of weird things like that.
Mm-hmm.
And so a question would be, why yeah. Well, and so you're saying that, I mean, standard inflation will surely make those go away because it dilutes them by some huge factor.
Right, exactly. You get an exponential drop off in monopole density, so they become undetectable.
Well, in other words, things become very smooth.
Yeah, I mean, just like with horizon and flatness, it's the same, smoothing effect. Yeah, and I don't know how we think about, magnetic monopoles in this context yet. I think
Well, I think, but okay. So look, the basic point is every coordinate is being everything that was at a particular scale. You know, the scales are changing. Why does that happen? What was a sharp domain wall becomes a very fuzzy domain wall because you basically just expanded the scales. But
right.
there's probably more to it than that. I mean, probably, one question would be in our models, there might be, one thing that doesn't exist in the usual case is more exotic, weird things in space-time, so to speak.
No, of course. I mean, there's bound to be a whole other collection of possible topological, defects and things that come from dimension change. But
right, and space tunnels and God knows what else.
Right. But in the interest, yes, in the interest of being practical, I was trying to focus on one effect.
No. I know. It's a good idea. I'm just trying to understand qualitatively, if there were those effects, what would their consequence for the existing universe be? In other words, let's say there were those effects and there was this dimension cool down effect, even though it seems to be a dimension heat up effect that we're seeing here. Well, there's going to be a theory of this. There's going to be a theory, and there's going to be some universal, somewhat universal. That's the question: is a lambda CDN analog for dimension change? All right. Well, good thing to figure out. And yeah, I mean, we need to this whole creativity of figuring out effects that might be there. Yeah, I wish there were. I mean, I need to go look up because I'm just desperately out of date. What's actually known about the cosmic microwave background? I mean, the temperature distribution on the sky is known. The polarization distribution on the sky is sort of known. Is that a true statement?
I think so. Yep.
And photons don't have a lot else that they have to. Oh no. The other thing that's known. The other thing that's known is it's a pretty close to a Planck spectrum. Is that true?
Right.
And so, Planck spectrum parameterized by temperature, suggesting thermal equilibrium in different directions, but with variation as a function of direction in the sky. And unfortunately, there's not a lot else a photon can tell you.
Right.
I mean, actually, there is another thing which I have never heard people talk about, which is polarization as a function of energy.
Mm-hmm.
That's a possible thing. And I suppose that's about it. And I don't know whether the temperature variations. Yeah, I mean that I know there's this cosmological perturbation theory stuff that allows you to compute those. Anyway, all right. Well, I shall. You should go. Sorry to keep you up so late. And,
No, this is fun. This is good.
Right. Well, okay, fair enough. And then we need to. Wow, this is a big. I just got this picture of the effect of placebo versus vaccine. And for the first 9 days, placebo and vaccine track 10 days actually. Placebo and vaccine track each other. So in other words, you don't actually get.
Yep.
And then they just peel off completely.
Well, it's a good sign, right?
It is a good sign, yeah. I mean, it's a little bizarre that time frame is comparable to the time frame that people get sick for. Like you were sick for like a week or something with this thing. Is that right?
Yeah. I think 5 days.
Right. Well, it's kind of weird that
Is that what you'd expect?
Not really.
Yeah,
I think they're basically unrelated issues because I mean one is the parading of the immune system past. I mean, I don't think the mechanism is, past the small amount of the stuff that you get in a vaccine. Yeah, I mean, my favorite computation about this whole thing, which I was embarrassed I hadn't done earlier, is that the total size of all virus particles that's infected everybody on Earth, you could kind of hold in your hand.
Right.
I mean, one of the things, okay, I'm going to disappear in a second, but one of the things that I sort of find interesting about all of the stuff that we're doing and so on is just these senses of scale, which one doesn't really have. And this question of, like, can our very solid seeming reality actually come about by these, very, I mean, okay, so there's a piece of intuition that people won't have had in the past, which is that, for example, I'm looking at my computer display. It looks like a picture of reality, yet I know it's made of pixels, just lots of them.
Mm-hmm.
And that's something that, I mean, again, I'm still interested at what people haven't been able to figure out. And I also, I'm getting more data, by the way, on that consciousness thing. I'm getting sort of more data on what, I mean, I kind of said, I have no idea what philosophers have said in the past about this. But it is interesting. I mean, Kant did surprisingly well. He got surprisingly far, and he figured out surprisingly many things. It's just like there were certain intuition blocks that they don't have. Anyway, okay, I better go to work here. I've been procrastinating all this time trying to finish this other post, so I better go.
Right.
Okay, to be continued.
Okay. Talk to you soon.
See you. Okay, bye-bye.